Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about the column space of the matrix A. So this is 3.1 in our textbook by Gilbert Strang, and let's take a look. So for example, let's say we have the matrix A is the vector 1, 0, and 2, 0. Okay. Now, let me tell you what, let's try this, and then we'll define the column space. So if I want A times X, well, that means this is going to mean that I'm going to have X1 times 1, 0 plus X2 times 2, 0. In other words, AX just means all linear combinations of the columns of A. Well, notice that I'm going to rearrange this one very carefully. I'm going to write this as X1, 1, 0, plus 2x2 times 1, 0. And then one more item. Let's write this as, I'm going to factor out the vector. So now I have the scalar of, this is going to give me the scalar of x1 plus 2x2 times the vector 1, 0. Well, what is that? That just means that the column space of A, is very simply the line described by the vector 1, 0. And that is the column space. So let's write that. The column space is, and we'll define it a couple ways, is the set of all is the set of all linear combinations of A. So the column space is the, actually it's not really, it is the set, but it's also it's the space and the set. So in our case, the column space of A, we'd say the column space of A is the line, and all we have to do is just give a vector. If we're talking about a line, is the line 1, 0 in R2. So look at what we had. We had two vectors, but we were only describing a one-dimensional structure. Only a one-dimensional structure. Now, let's try this again. Now, let's say that A is, let's expand it a bit. We'll call it A prime. This is 1, 0, 2, 0. And then let's put a 2, 3 in the third column. Now, look at this. We know that 1, 0 and 2, 0, these are dependent. These are dependent vectors. So they don't add anything to the space that we can describe. So what does add dimension is an independent vector. And why do we see this? We can see that clearly 1, 0 and 2, 3 are linearly independent because there's no way that you can multiply 1, 0 by a scalar and get a 3 in that second position, because nothing times 0 will give you a 3. So these are independent vectors. Well, if you have independent vectors, then what we can do is we could say that I could take my A prime times X. Well, the linear combinations are X1 times 1, 0 plus X2 times 2, 0 plus this one's X3 times 2, 3. Well, we said that these two just created a line, but now we add another line. So if we have two different vectors, what do we have? we have a plane. And so now we can say that the column space, let's just write it, let's use the notation that column space of A is a plane in R2 because there's two components. Well, a plane in R2, i.e., the column space of A is R2. Now, that's the idea behind the column space, but let's take a look at one more example. So here we go. I'm going to move up my screen. And let's take a look. We'll call this the matrix B. So B will be the vector of 0, 1, 2, 1, 1, 1, and then 1, 2, 3. That's the vector of B. Okay. So notice this. Notice that we have this third vector is just the first, it's just the first column of B plus the second column of B. So it's a dependent vector. It adds nothing to our picture. But what creates the picture are the first two vectors, the independent. So this third one is dependent. We already showed how, because it's just the sum of the first two. These first two are clearly independent vectors. They're clearly independent vectors. Well, what does that mean? But notice, though, if you have two vectors, then you need two vectors to describe a plane. Okay, where is this plane? Well, because the vectors have three components, the plane is in R3. So we can say that the column space of B is a plane in R3. Now, a common mistake here is to say, oh, well, plane, that's R2, that's R2 in R3. And that's incorrect, because remember, something in R2 only has two components. We're talking about a space now where everything is 1, 2, 3 components. So since there's 3 components, it has to be in R3. So we would say that the column space of B is a plane in R3. Now, another way to look at this is this. So we said it's all linear combinations. Another way is to look at the matrix equation, AX equals B in general. So if, let me use this is a big one. So we'll do this. Consider this. So consider AX equals B. That's the matrix equation. If AX equals B has a solution, then what would happen? Then B is in the column space of A. Now, will it happen that sometimes there is no solution? And the answer is yes. And so when that happens, if B is not in the column space of A, then AX equals B has no solution. Has no solution. So here would be an example. So let's try B prime. Let's get rid of that dependent column. So we'll say B prime is 0, 1, 2, 1, 1, 1. And we want to solve B prime, capital B prime times X equals the vector of 0, 2, 3. Well, in other words, we need a linear combination that says x1 times 0, 1, 2 plus x2 times 1, 1, 1 has to give me the vector 0, 2, 3. And you can see that the problem here is that in order for this to work, my second x2 for the first one, it has to be 0. It's the only way, because we have this equation x1 times 0 plus 1x2 has to be 0. Well, then this just means that x2 here has to be 0. Well, if x2 is 0, then there's no way that we can solve this problem for the rest of these. So that's why that doesn't work. So when there's no, so in other words, we would say that b prime x equal 0, 2, 3 has no solution. Or has no solution. Or likewise, you could say that b is not in the column space of b prime. That's the first part of the matrix equation that we're going to study. And also notice this, we've been working with 3 by 3 matrices, but b prime was a 3 by 2 matrix. Well, that means that this vector x here is a 2 by 1, not a 3 by 1, it's just a 2 by 1. And so we're going to, as we move forward, we're going to start looking at what happens when the number of components in x start to change a bit and what kind of pictures that we see. Thanks for watching.